moi, je suis de Champagne. C'est différent. C'est différent. C'est différent. Mais en Champagne, il doit y avoir aussi des Chinois qui travaillent pour les échanges de Champagne avec la Chine.
Oui, il y a pas mal. Les systèmes sont spéciales. En Bordeaux ou en Champagne.
Ma sœur a travaillé dans une grande maison de Champagne.
Pour la présentation, Clément, il faut que je partage quelque chose ou c'est fait automatiquement?
Non, en fait, on voit les
Parfait.
Du vin. Non, c'est le du, c'est la partition. Le nom, c'est vin. Je bois du vin. Et je vends du vin. Et j'achète du vin.
C'est les cours de français, on est dans quel?
Je pensais que vous vouliez du vin encore.
Enfin, présent.
Oui, tu es en direct. Pictures of the star.
Oui.
Ah, c'est déjà en ligne?
Oui.
Ok.
Oui, comme ça, le test pour être sûr.
Parfait, merci.
Il y a déjà 3 personnes.
3 personnes. Les gens me voient. Ok. Ah. J'ai une question. Bon, je vais un peu. Bon, déjà.
Je pensais comment il va. Ça va super. Bon. Je suis arrivé. Voilà, il y a quelques minutes. Je vais pouvoir accepter. Bon, on fait le là. Faites les règles. J'espère que c'est bien.
Vous avez un post-doc après? Vous allez continuer après? Comment? Vous allez continuer comme enseignant après?
Non, c'est juste embauché à côté de
Ah, vous allez. C'est bien.
c'est une thèse.
Ah oui.
Donc, c'est bon. C'est ça, merci beaucoup.
C'est un peu différent. Oui, c'est ce qu'on m'a dit. Non, il y a des autres jeux, pas ouvertement.
Jean?
Okay. Good morning, everyone. So we are here today for the PhD defense of Estevan Tu. So the title of this PhD defense will be high performance for generator. So we have 45 minutes, but before I'm going to introduce each member of the jury in order you know who you are going to talk and evaluate the work. So I'm going to start with the two reviewers of your manuscript. So we have Professor Domenico Zetto from I don't remember the university where you were originally from, Domenico.
AGH, University of Science and Technology in Poland, in Krakow. Poland.
Okay, from Krakow. That's the university from Krakow. Sorry. Your second reviewer is here, Professor Hervé Barthélemy from University of Toulon. Very good. That's okay. Then we have Dr. Thomas Beauchesne, who is from NXP Semiconductor, the company within you get this joint PhD work. Then we also have from this company your supervisor. So we start with Stefan Tu, who advised your PhD from Toulouse. From the academic part, we have Manuel Pistono, assistant professor from the University of Grenoble. Your supervisor, Professor Jean-Baptiste Berger from the University of Bordeaux. I think we have everyone. And the last one, I will head this jury. I'm territorial professor at Mathematica, where you studied to when you were in Bordeaux. Is it okay for you? So 45 minutes, and after we're going to have same time for a question and answer, right?
Okay. place for the presentation. And thank you everyone for coming for my PhD defense. So to start, this is the agenda of today's presentation. We will start from introduction, context, going through some theoretical part of the oscillator phase noise, then on the designs of the ball-based complete oscillator and also for the cross-couple oscillators, and last on the tape-out and measurements of results, and to conclude some conclusion and future perspectives. So from the introduction, radar systems are increasingly used in autonomous vehicles, industrial sensing and monitoring, and also in emerging IoT applications. So where the RF signal is very critical here and plays an important role. So just an example, here we have the FMCW radar, which is used in the radar technique for short to medium range sensing. And its performance is strongly limited by the local oscillator, such as the frequency linearity, which is related more to the accurate range estimation, and also on the phase noise, where it is used for the dynamic range and measurement accuracy. One of the most common ways to design a local oscillator is by using the LC tank as the resonance circuit. However, it has a low Q factor. The inductors has a large area, and we have the nonlinearity due to the coupling and parasitic response. So for this work, we use the Ball resonator, which is the Ball acoustic wave, for some of the main reasons that we can list here, due to the high quality filter, which can have around 500 to 2000, and also the operating frequency, which goes beyond 2 GHz, compared with the Soul resonator that's below around the 1.5 GHz. It has a high frequency stability and also strong wave confinement, which allows better power handling capabilities. And also in this case, we have improved thermal stability. So in terms of the ball-based oscillators, the existing ball-based, they are not fully exploited in terms of the frequency design methodology. And also there is a lack of approaches that links directly the resonator properties to the oscillator level performance. So in the literature, we find most of the oscillators in forms of CMOS cross-couple, NMOS cross-couple, and also NMOS colpits. However, in this work, we have seen that the PMOS cross-couple and the PMOS colpits using the ball-based resonator, they have better performance and promising results. So in terms of the technical objectives for this work, we want to target a frequency around 2.42 GHz with a phase noise at 100 kHz lower than minus 130 dBHz, and for 1 MHz offset lower than minus 150. With a core power consumption lower than 2 milliwatt, and the FOM figure of merit, which is given by this expression, is an FOM largely used to compare the oscillator topologies to have higher than 220 dB. It's a state-of-the-art target, and while keeping the die size lower than 1 millimeter square. So in this work, the application is to use the Ball oscillator as a part of a DBS structure. However, the DBS itself is out of the scope, so we are going to focus for this thesis only the Ball oscillator. In terms of the oscillator and phase noise, giving a little bit more of background before entering on the design. So we have a linear theory for the phase noise, which is the impulse function, the ESF given by the expression. In general, the idea is that it captures the phase sensitivity. As we can see from the expression, the phase deviation is the integral of the ESF times the input noise. And I'm going to go through the details of this mathematical theory, but which is from the Professor Hajimi. The phase noise expression and the 1/f square region, which is dominated by the white noise, is given by the expression. As you can see, the RMS value of the ESF is logarithmically proportional to the phase noise, and also it weights how the white noise, which here we have the PSD or spectral density of the white noise, how it converts into the phase noise. So samely for the 1/f cube phase noise region dominated by filter noise, we have the DC value of the ESF, which is logarithmically proportional to the phase noise expression, and it weights how the filter noise converts into phase noise. On the other hand, we have the PPV, which is the perturbation projection vector. It's kind of the same idea, but it's a macro model based on floated vector theory. It captures in this case our state of phase sensitivity. The phase noise deviation expression is given by what we call here the PPV component times the input noises. So in this case, the PPV component is a floated vector times B. With B is a matrix, a vector that captures, that links all the input noise sources through the state of the oscillator. And the main idea is it is a very mathematical and complex theory. However, Professor Levantino proposed a frequency domain extraction, which allows us to extract directly the PPV component. And this extraction is available in the standard RF simulation tools, which we are going to take advantage of it. And it avoids complex mathematics while keeping the accuracy of the original mathematical approach from the floated vector theory. So what I want to express is that the ESF and PPV, the ESF is a more scalar function linked to a single node and a single perturbation analysis, and it's normalized to the EV charge injection. However, on the other hand, the PPV is a more vector micromodel for the multi-nodes and multi-source analysis that allows all state variable sensitivity in one analysis. So the idea is that the ESF is a special case of the PPV when we restrict for a single node and single perturbation, and that the ESF is proportional to PPV due to the difference of in terms of the normalization of both theory. So for this work, we take advantage of the RF simulation tools such as Spectral RF, where we can extract the PPV component directly. However, instead of using following the mathematical interpretation of the PPV, we can analyze a single node through it and use the ESF theory for the interpretation, as explained before in the previous slide. So also in terms of, before going to design, some comments in terms of how noise is converted into phase noise. So we have the listen effect, which is a linear time invariant theory, which is presents a 1 over f square factor from the noise through the output noise that we have the phase noise. And we have also the up-conversion mechanism, which is a more time-varying analysis and interpretation. The idea is that the oscillator behaves like a mixer due to their present here have a couple structure, and the switch transistor behave like a mixer. And we have also the tail current noise with through the tail current transistors acting as a single balance mixing to this structure. And the baseline noise, it is translated from the baseline to the carrier. So in terms of these, we have two conversion mechanisms, which is the AM/FM, which is where we have amplitude noise converting to frequency variation. In this case, is due to the nonlinear capacitance. And we have the AM/PM, where we have the amplitude noise converting to phase delay, and it is more in this case due to the nonlinear switching of the transistor, their harmonics, and also the bias noise. It's a simple representation of how the noise are, in this case, baseline noise up converted around the carrier, and also the higher harmonics noises that are down converted around the carrier due to this conversion and down conversion mechanism. So going through the ball-based Colpitts oscillator design, before entering the design itself, we speak a little bit on the methodology and how we approach the design process. So we use the GMID methodology as a core design tool. It is defined as the derivative of the LM of the drain current over the derivative of VGS. So the interesting of using the GMID methodology is that it links directly the power with the gain and the speed. And from it, we can obtain directly the information of the inverse region that the transistor is operating, such as weak, moderate, and strong. It is technology dependent. In this case, we are using the 28 nanometer, but it is model independent regarding of the model of the technology that we are using. Another point is that since we are using short channel transistor, the famous square law transistor is it doesn't work well since it fails starting from moderate inversion, and in this case, for the GMID approach, we have a better model to understand the behavior of the transistor. And we have many key figures of merit regarding the GMID methodology, but in this case, we take approach of the normalized drain current. And as we can see here, we have the normalized drain current as a function of GMID. From the curve, we can have easily, and its value, we can have understanding on the inversion region that the transistor is operating. And for instance, if we define a GMID value and transistor channel length, which is related more to the transistor inner properties, we can use this chart to define to obtain the transistor width for the targeted operating conditions of the transistor. In terms of the ball resonator, we use the modified Butterworth Van Dyke equivalent electrical model, which is a one-dimensional model to implement the ball resonator in the design. So here we have the schematic, and we have a motional branch formed by RM LSCM, a static branch due to the dielectric resistor capacitance, and the series resistance, which models the electrical loss. The ball resonator has a particular behavior. Here we have the normalized impedance, and it has two resonance frequencies, one FS and FP, given by Ball expression from here. And the interesting thing is that here the LMCM resonates for FS and LMCM and C0 for FP. In between FS and FP, the ball resonator behaves as an inductor, and outside of this frequency range, it behaves as a capacitor. Another interesting point is that the maximum quality factor of the resonator, it's neither at FS nor at FP. It is in between both and closer to FS. It's also another point that we have considered for. In terms of the structure of the Colpitts oscillator, we have plenty of designs using the LC10, and normally they are using in a drain to source capacity feedback. Here we have the L with the capacitors for the resonance, and in the case of ball-based Colpitts oscillator, we use in a gate to source capacity feedback. So then we can use one ball instead of two resonant circuit. So in terms of the structure that we are applying, we are adding a cross-coupled pair to boost the negative conductance seen by the ball resonator in order to alleviate the power consumption and also the startup constraint. In this case, in the left part on the C topology, we have gate to source GM boosting feedback, and here on the D we have a source GM boosting feedback. So we have two ways of calculating the cross-coupled pair. For the C1, the negative conductance boost part is 1 plus GM3 over GM1 times 1 plus C1 over C2. In this case, the difference is on the last part. However, since we are using the GMID methodology for the design, the GMID value fixes the VGS of the transistor. So if we can see from the gate to source GMID, the gate of M4, they are connected to the gate of M1. Here, higher gate value. So therefore, for VGS, we have a higher source. Therefore, leaving lower voltage room for M1 and M2. But in this case, since the M3 and M4 gate, they are connected to the source of M1 and M2, we have lower gate value and therefore lower source value, allowing higher voltage headroom for M1 and M2, but while keeping the needed voltage for the current transistor. So in this case, we proceed the design using NMOS colpids and also PMOS colpids with structure source GM using feedback. Therefore, of the main capabilities for this PhD work, on the left side we have the NMOS, so it's a gate colpid gate source capacity feedback and a source GM using feedback. So for the PMOS, it's the same, the dual when compared to the NMOS one. And we have done some approach on the voltage lag optimization is that the NMOS topology, the gate is connected to the DD and the PMOS, the gate to the ground. Also, in terms of the technology choice, we use the M1 and 2 transistor and the current mirror using thick oxide devices. They are bigger devices, they have lower noises, but however, they have higher VTH and VGS. And for the thin oxide devices, we use the GM-using pair, since in terms of the noise, they are less important in our analysis. So if we are using it in the oxide structure, with a lower, as they have lower VTH and lower VGS, allowing more voltage headroom for the main structure, which is the M1 and 2. And in terms of the phase noise modeling, actually in the literature, there's no explicit approach of phase modeling for the low-base piece of scale. So in our work, we have obtained a phase noise modeling for our study oscillator. It's based on the work of Professor Andriani for the Colpids oscillator and Professor Fiorelli, which is the so we have here analysis. We use here the NMOS Colpids oscillator, and for the analysis, since it is symmetric, and just take half of it and analyze how the noise, in this case the white noise, is injected in two of the main nodes that we are analyzing, the A, which is at the gate of M1 and 2, and the B at the source of M1 and 2. Since the ESF is related to a single node, so we need to write the analysis for each node. So here we have the white noise from the ball injecting at A, and now here, for instance, here the drain source conductance noise injected at node B, and for the battery capacitor. Enter in the details, but from our analysis and obtain expression, the 1/f square phase noise, we have expression, a big expression, but I want you to note is that here we have the ESF, RMS value for the ESF, for the node B, and RMS value for the ESF node A, and also we have after we will this expression and the GMID as which is logarithmically proportional to the phase noise expression. And similarly for the phase noise region, we have also the GMID and also the DC value of the ESF. And we develop it. We have the GMID, the square, logarithmically proportional to the phase noise. So before presenting also the design the methodology that we have used, some important notes of the phase noise trade-off is that in terms of biasing and the feedback ratio, we are biasing optimal F1, our optimal phase noise. The first one is in the condition where M1 and 2 transistors are in maximum saturation without entering triode during the oscillating period, which allow us to have lower noise conversion due to lower nonlinearities, and this is other current. This balance is phase. In this condition, we have oscillator in between the current and voltage limit boundaries, and in this case, the oscillator has the maximum amplitude, but it requires higher current to obtain the best phase noise. For the capacitive ratio, we have either a higher ratio or a lower one. The higher one allows to achieve higher amplitude for the same current. However, those faster in the triode region presenting higher nonlinearity and high noise conversion. For the lower ratio, we need higher current to achieve the same output amplitude, but that allows the transistor to stay longer in saturation before entering triode. So we have a higher linearity and lower noise conversion. For this work, we choose for the oscillator to create at the optimal FOM and C1 equals C2 for a lower end ratio. So for the proposed design methodology, here first we define the minimum GM with a safety margin. You have seen that the GM has a big impact on the phase noise, so we need to keep it. And the second part, determine the oscillator V out in order to be correct. So then we have the GMID. We choose a transistor L since it is also related to the transistor properties. So therefore, through as presented before, the normalized drain current chart, we can also the width for the desired operating condition. And then we can check first if the transistor bias condition is okay. We can go back on the first point and redimension the GM value. Later, if it's okay, we can go through the oscillator operation. If it's operate in the condition that we want, in this case, the optimum F1, we can proceed. Go back on the part, layout and ID. And then lastly, we can check in terms of the phase noise performance. So here, a bit on the oscillator layout. So the schematic of the simulator circuit is the ball. The idea is the ball will be external to the die and wire bonded on the chip. So it's plus the current mirror. That the auto signal goes through a capacity value which is around 50, just for AC. In this case, with the buffers, which are the CMOS inverter, and then the output signal is wire bonded again outside for measurement. So here we have the oscillator layout, mirror, and also for the buffer. So in this case, for the NMOS, it is actually the same since we're using the same layout approach, and the circuit we are optimized through differential similar and also we have identified RF nodes to optimize the circuit operation, and also some device layout optimization were also done. In terms of the post-layout simulation for the optimal FOM, so here we have the phase noise simulator. The phase noise between CMOS at 100 Hz, we have a difference of around 4.4 dB, better for the PMOS, and also a difference of 3 dB. So if we have an advantage for the PMOS of around 2.7 dB and 2.6 dB and 1.4 dB for 100 kHz and 1 megahertz of frequency offset, respectively. So, on the chart, we can see the difference of the phase size. So we have a better performance from the PMOS oscillator in the post-layout simulation. So just some comment of the ball-based cross-couple oscillator in order to have some comparison. I'm not going to enter into the details since the code is our main technology. So we have here the NMOS cross-couple oscillator. The B part is the PMOS cross-couple. Here they follow actually the same idea for the design. So we have the ball resonator, which is wire bonded to the circuit. We have a cross-couple pair, the PMOS and NMOS, provide the negative conductance for oscillation. We have a CD capacitive tuning to provide the capacitive load. We have a CS capacitor acts as a DC decoupling in order to avoid the DC instabilities. We have a common mode feedback transistor to provide differential stability and also the bias by the corrector. So following the same phase noise idea that we have presented for the colpits, we have arrived the 1 over F phase noise region, which we have also the GMA as a key parameter, which is logarithmically proportional to the phase noise, and also here we have for the 1 over F cube region, also the GMAD. So in terms of the phase noise results, here we have PMOS and the same for the layout approach. What interesting from this phase noise result is that for the lower frequency offset, cross-coupled performance, and for frequency offset, we have the coupled better phase noise performance. So here we have a chart comparing the results of post-layout simulation for the cross-coupled and the colpit. The main idea is that if you compare the figure of merit between both, we have better performance from the NMOS one compared to the cross-coupled. So actually, this result leads us to choose the colpit oscillator, both NMOS and PMOS, for the tape-outs. They have the superior performance when compared to the cross-coupled. So entry for the tape-out and measurement results. So here on the left we have the die, the PMOS. If you see for the NMOS one, it's very localized. In this case, the layout is has 0.71 millimeters square. Since we have a space on our chip, we have actually 6 circuits. So here we have the PMOS colpit oscillator, the NMOS colpit oscillator, and here we have some variation and allows for further analysis. In terms of here we have the PCB we have designed with the tree for supply, the shield you can see here, and both the die placement. We designed a member for the balloon, which is 50 ohm, which transforms the differential signal for a single one for measurements. We have one on the circuit for the PMOS and the NMOS, and a zoom view of our circuit. In terms for the measurement test bench, we use the RNS FSWP for the phase and also the for the supplies. How the system is optimized for measurement and analysis instruction by using based code. We use UT inside the Faraday cage for since the frequency is close to Wi-Fi and Bluetooth in order to avoid interference. For the temperature measurements, we have a construct one circuit tailored for our application, which is based on the Peltier module, where we can extract the heat from one point and another. So therefore, keeping it cold, either cold or hot. And all the temperature control system is optimized through a P controller, which is a Python code base. It's for control, reading, and also measurement with the FSWP. A little bit more of some measurement secret of our temperature control system inside the Faraday cage. And here's some photo of the measurement setup. For some results for the root temperature for the PMOS colpit oscillator, here for a VDD of 1.45 and a current of 1.25 milliampere. At 100 kilohertz, we find DC hertz, and at 1 megahertz of offset, we have around 159.4. For in terms of the spectrum, the first harmonic, it has around 60 dB of difference between the second and third harmonic, showing a very clear spectrum result. And in terms of the going further on an analysis, we have switched the bias from 0.9 to 1.4. Beyond this value, we have SOA, which is a safe operating area of the transistor. So we keep until 1.4. What I want to note from this chart, on these results, is that the phase noise, we have the optimum around 1.2 for the NMOS and 1.25 for the PMOS. And we, as you can can see it arrives as at a lower stable part of the result, and this is due to lower noise conversion. Since we keep the M1 maximum saturation, therefore lower noise, and also then deep saturation also then lower non-linearities and therefore lower conversion. Here, in terms of heat merit, to reinforce the phase noise result, so we have a close peak near 1.2 milli ampere and the PMOS 1.25, showing that here we have closer to the peak point and showing a good trade-off between stability. In this case, we have also the behavior validated in terms of post-layout modeling, showing a good trend in between measurement and simulation. So last part on the in terms of the temperature measurement, for the frequency stability, we have in the NMOS oscillator we have around minus 0.96 ppm per degree Celsius, and the PMOS minus 0.35 ppm, which is very low. So two of the main reason is one from the from the software, it has a low coefficient, and also stability of the oscillator in terms of the frequency oscillation. So for the phase noise behavior, we have used in offset at 10 kilohertz and 100 kilohertz. The phase noise reduced close to 60 degrees, and then it stabilized and also increased a bit. This is due to the resonator-induced noise. So it reduces until 60 degrees, and after is the noise from the active devices start to increase. And for the far out phase noise, we have at 1 megahertz and 10 megahertz, which increases with the temperature, which is due to the thermal noise of the active devices, of the transistors. So we had encountered one problem on the design and also impacting our results is in terms of the ESD pads. Since the pad ring that we are going to have a ESD circuit. So the problem that we encountered is that we have the case without ESD pads and here with the ESD. So first point is that we have to encounter a bias shift. We are going to see on the next slide. And also we have impact on the phase noise performance. We have degraded our phase noise performance and reduced the difference between the NMOS and PMOS results. So we have lower advantage due to the ESD noises that have been impacting our results. And also, of course, the degradation of phase noise, we have also the same impact translated in the figure of the rate. So in this case, we have a performance degradation due to the ESD pads. And why? Because we have the ESD pad have so it's in part and it's connected to the PCB, and we have two outputs. We can either use one or the other. So the first part we use normally for the RF signal, second part for the PCB. So the problem we have encountered is oscillation amplitude reduction as the diodes conduct a bit during the oscillation period. So therefore, we need higher bias to achieve the desired condition for the oscillator, and also we have noise coupling from the diodes due to the substrate. So as you have seen, we have less phase noise difference between NMOS and PMOS because PMOS oscillator has a major impact since their gate is connected to the ground. So here we have substrate coupling with the diodes. There's another problem for the DC current limitation is due to a resistance of 1.2 kilo here that for the passing by provides a high voltage and in terms of the diodes. So that's 3 problems that we encountered. But just to conclude this presentation, here we have the state of the art for the ball-based oscillator. So we are the first reported nanometer CMOS ball-based oscillator, and if we compare in terms of the F1, 100 kilohertz, to the other words, we have the third best, so behind Kaya and Ma, so 100 kilohertz for the F1. But we have at 1 megahertz of F1 and phase noise, we have the best reported in the state of the art. And another important point is that for our work from Calisman, we have ESD pad strictly integrated, so passing by industrial validation. However, for the MAP, which has the best F1 at 100 kilohertz, there are not explicitly integrated. So to conclude, we had a comprehensive framework for data design, where we use GMID as a key design parameter, and we have presented and studied phasors minimization approaches. And here we have presented also a systematic methodology for design. Here presented PMOS colpits as one of the main topology of this work, presenting low power, ultra low phase noise operation. We had a good agreement in terms of the modeling on the results. And we have a robust performance across temperature variation as presented. In terms of the state of the art, we are state of the art results, especially for at 1 gigahertz of frequency. In terms of the targets that we had defined at the beginning of the presentation, we have achieved the targets that we had defined in the beginning. For the future perspective, 4 points. The first one is the ESD pad redesign. So what we can improve is to especially present the swing of the oscillator, adding diodes on parallel, so that we allow a high voltage swing before turning on the diode, and also limit noise coupling by avoiding the transistor gate connected to the ground. In terms of the bias layer, here for the current mirror, we are using a ratio of 1 to 1. So maybe we can improve by making it 1 to 2 and pushing lower current from the process. For the packaging strategies, we can also start to think how to integrate the ball resonator into the chip. For instance, there are free chip approach, but also continue the work on starting this part. And the system integration, of course, integrating the balls later into a more level radar system, such as the DDS presented in the beginning. For our PhD, we have presented 3 works: the ECI International Conference on Electronic Sequence Systems at Marrakesh and NC, and also one for Prime in Taormina, Italy. And we are preparing one journal submission, especially for the PMOS colpit result measurement for either TMTT or TS. So thank you so much for your attention. And if you have any questions.
Thank you very much, Esteban. So we take a break process, and then we're going to start the Q&A time. Yes. So I give the floor first to Professor who was a reviewer of the manuscript.
First of all, I would like to first of all, I would like to congratulate and also congratulate your other co-directors. So it has been massive and work from the very beginning. And so it was very, I really enjoy reading the thesis. I also noticed that somehow strong bond with our work, what you have done before, and you advanced that work specific implementation with the filter. president. So congratulations for that. So you have already received some of my questions. We can restart that and those questions or comments. I don't know how much time we have. I have other few curiosities that is possible. Otherwise, for the end.
Okay. Okay.
So it won't be possible to answer all questions I have in mind. Maybe I will follow up for me to get a better understanding of something. Yes. So I need to focus on.
We have 1 hour for the whole.
Okay, so what?
But because you were.
Okay, so so we can just break the ice.
Yes.
With the questions, with the comments you received together with the review.
Yes.
The first one was sorry, I noticed that you already answered some.
Yes. I took the question as the base from both professors to develop the presentation. Yes.
So I would skip some of them because they are more related to writing.
Okay.
We got to, how did you sort out this story of what you call normalized in the sense that you used in your thesis is J divided by W.
Yes.
And W over L is a dimension. So with no dimension.
Yes.
And then overall, you use J, which is actually a number.
Yes.
Yes. So I would like to understand how if it was true that this was the paper on 49.
I think
I didn't have a chance to read that paper. So you can comment on that.
Yes, that's a very important point because actually it's not J, so it's a big confusion I made. So it's really the normalized current. So it's not the J, the current state. So it's more like a normalized J. So it's a dimension, and it's not really the. It's correct. Perfect. Thank you so much.
And this was made in this paper in 49.
Yes.
Was reported
as normalized current. So it was more maybe when reading multiple papers, I made a confusion. So it's not really J. It's really as you mentioned, Professor. It's,
so 49 was correct.
Was correct. So it was I made a confusion. Yeah.
So when I was reading, because I didn't have a chance to go through 49, I thought that in 49 they came up with this and you just used that.
No. It's they came up with the correct thing, and I think while you're reading multiple sources, I mix a bit on terms of the notation. The idea is correct. Just how the name that I used was incorrect.
You know, one of the typical things happen in literature. Someone defines, and then many others use that. They really go through that.
I agree.
So if it was ID over WL,
yes, it's a normalized current.
Then it's the normalized density. So it's a current density because it's the current divided by area.
Yes,
it's a density.
Yes, but as
in this case, it was W over L.
Yeah, exactly. So it's a normalized current.
Thank you very much.
Yeah, thank you for that.
We can skip also the other question. There was one question about the power consumption of buffers.
Yes.
I haven't seen it even in the slides because maybe I missed. I was looking into something else. Can you just give me an idea what was this concept?
Yes, so the buffer actually, in this case, as also with the ESD pad, they're more for measurement purpose. So yes, exactly. And so normally the power of the buffer we are not taking into consideration in the FOM analysis. So that's why also most of the papers that for oscillators they don't.
No, that is absolutely fine.
Yeah, okay.
So no, it's not that the point. The point is how much power do you use?
So the buffer. Let me go back to better explanation. Let me go. The topology. Here, it's better to explain like this. So normal, the VDD is around 0.9 volt, so different from the VDD of our core oscillator, which is 1.5. So here 0.9, and it consumes around 9 to 10 milliampere. So around 10 milliampere, yes. Yeah. And since it's for measurement, so we allow a bit for yeah. And also one other point is it consumes high for to have a signal since also for measurement purpose, the input capacitance for AC coupling it's very low, around 50 femtons, because if we use a higher value, it will load our resonator and it will shift the frequency. So it also another reason. So lower capacity, we have lower signal arriving, so therefore we need a little bit higher amplitude. So that's one of the reasons for the 10 milli by the buffer.
So in moving to the next question, there was a bench schematic which is actually
this one.
We can keep this because it's correct. So it's when you connect this with the wire bonding to the bow filter.
Yeah.
And the question is, I noticed from your images that it's very you place the bow filter close to the chip. So the wire bonding is pretty small in terms of length. You have still 200 picohenry of over inductance.
Yes.
And what? And I know also that you use the classical gold. So the quality factor, consider the quality factor, which is typically around 25 for gold in these conditions. For this kind of is that correct?
Yeah. So I very interesting, important question, Professor. So I will use this one as to explain. So why most or even in every schematic I have the wearable as in it's less for the voltage, but for the cross coupled, the inductance from the wire bond actually can present parasitic resonance with the capacitors or loading capacitance. So it's always important to include it on the analysis. And here we have around 1.2. So it's because first of the distance, and also actually we try to keep it lower. So on here in the input is around, I think it's 300. So it's a lower, and the output since we have a longer distance to wire bond, it has around 1.2. And in terms of the material we are using, actually it's not defined. So from NXP we have a group. So I before starting the PCB layout, actually I have contacted so the group from NXP that they are specialized on the wire bonding part. So we keep in touch and everything for the modeling, how to place the die for the wire bonding and everything. And also the material they recommend me to use the one also for the lead, I think it's the name, for the wire bonding. So it's actually something that's wasn't me that defined.
Absolutely, so no, I fully understand that. I see now.
Yeah.
But the real question is that in in this schematic you show, they
Okay, yeah.
and only the capacitance and inductance value was not ready to a level, but doesn't matter. So you estimated that in some way. In general, this is depends on the frequency. But everything should be around 0.9, 1 nanometer, 0.9 millimeters.
Yes, around, yeah.
It's quite a lot.
Yeah, exactly.
But the quality factor, I haven't seen I didn't get if you when you simulate it, you consider the quality factor of the one or just the inductance.
Yes, now I get the question, and it's very important also. Not directly the Q value, but expression for the loss.
So you included the loss.
The loss, yeah, the loss.
Okay, this was
okay. So the loss is estimation from the distance value, so the distance and ratio. So yes, because we have since I kept in touch with speaking for the wire bonding, they provide all the information also for the width of the wire bonding. So then I include not really the Q value, but the loss, which is the same actually. Yes, exactly. Yeah.
So I think you also show me, give me an idea of which terms you are targeting, and it's fine. So maybe if you have any considerations that you would like, I can try. If you are still in MTT or TCAS, we can have a follow-up discussion.
Please.
To publishing is getting very difficult.
Okay.
Yes. Great.
Yeah, thank you.
So I had a few questions. If you have a few more questions.
Yes, please.
So let's start from the which is somehow related to
the resonator
question we were the last point we were addressing. One thing is that you mentioned that the quality factor of the resonator is between 500 and 2,000. This is the open load.
Yes, so unloaded.
Unloaded, exactly. So in the reality, when we put things together, so the wire bonding, the losses of the wire bonding, the losses of the output, what is in the end the load factor of this filter? Why I'm asking this question? Because obviously you have to make a specific choice. And the results that you obtain, they say that you were right. So to make this choice, rather than having something monolithic, to use an external device to reach the minimum phase noise in the best form, right? So the results you achieve have justified this. But what I'm saying is that your results are definitely better than the state of the art. Do they see the largely what is achieved with monolithic solutions? In other terms, in the end, from the evaluation of the quality factor, you can now a very important conclusion here. So how valuable is to go for an hybrid system compared to what you can achieve monolithic implementation? And the monolithic, assuming that the monolithic implementation would be still useful for your specification. Would be that something that can be pursued, or it's definitely out of range. You cannot reach your specifications. You need necessarily to go for something hybrid Yes.
So the monolith that you mentioned is kind of, for example, integrating the board inside the die. Is that correct?
No, I mean, you can think for the future work as your work can through some chip, but I was not intending in that way. I was intending monolithic in the sense that using traditional spiral inductors, coupled inductors, and so on.
So yes, if by using, for instance, a resonator inside a analytical result, we can optimize for the case, but not achieve such a lower phase range.
What is the load that you estimate the load to
It's with around 10 to 15.
10 to 15?
Yes.
But this is something in the range of in the range of integrated LC filters.
Yeah.
And so I assume that you probably get a much better quality factor than 15.
Yeah, but you won't reach how we can reach in terms of a ball in this case the ball and the saw. They are acoustic resonators, so they have a really high quality factor in the hundreds. Even with a loaded case, we are hundreds or even closer to 1,000.
Okay, so now it's you not be 15 because otherwise.
Yes. For the ball, yes.
Yeah,
for the ball, yes. Yeah. And so that's why also very important remark, Professor. So that's why also here I added this. So for the quality factor, I couldn't really put the values for the NDA because the ball is from a supplier, it's not from NXP. So that's what I wanted to show is that if we so the quality factor is also depends on the frequency. So how the resonance is loaded, it will impact so and also in terms of the resistance, everything. So a lot of things to play, but we are still in the close to the 1,000, close to 1,000.
So based on this evidence of yours and based also on the discussion, I think this is something that you should clearly point out in your future paper. You say if you want to reach this level of performances, you have necessarily to adopt this approach compared to the others.
Yeah. So I agree, but there's just a kind of a nuance, is that for example for the state of the art, most of the papers they don't really present the Q factor value of their work. I think one of the reasons the NDA, but for instance, since for example for I think it's from Kalia, she's from another company, and their company they produce their own logo. So therefore they can present a lot of information, very details on how the ball is worked on and even the quality factors. Yeah, that's
going to the specific aspect to circumvent regarding the idea. It's just a discussion to make this clear to the reviewers of your paper, so that if you want to get to this level of performance, this is the only way for you to do it and accept hybrid integration, because with integration here. So,
you can optimize, but never go through that level.
I think this is a distinctive character of this work, because imagine the case that you decide to go all to these steps regarding the fact that the methodology will be applied with the case and so on, and it's always fine, perfect. But in terms of implementation, which is what you are going to then to report on the paper, because you will focus on coordinates, you still need to justify that approach. In the end, was this approach justified? A way above you can get with way better you can get with the monolithic. Yes, so this is the way I'm presenting this favor. And this is the way why I ask you to accept it.
I agree. I totally agree on this approach.
Okay, so
Make it clear.
It's a kind of a
Yeah.
backward.
Yeah, back engineering.
backwards,
Yeah. Thank you.
Okay, so I was told that there is nothing more to no more time, so okay. There is one aspect that I missed, so I will I have still two curiosities.
Yeah, please.
But I will pick up just one. There is one aspect. Why the impact? You explain on slide 36. You explain that the SD pad had a higher impact on the PMOS.
Yeah.
And the question is, in the next slide, slide 37, you try to explain that, but I missed it. Why this impact is higher for the PMOS rather than the...
Okay, so first, just quick view on the structure, maybe go a little bit fast. Is that to allowing a higher voltage headroom, since we are working from 1.45 for 3 stacker transistors, here, and also the GMID is the VGS. So if we can lower the gate value, we can also lower the source in order to have a higher voltage headroom. One of the approaches is to connect the gate, the PMOS, to the ground. So you have a lower gate, therefore a lower source and allowing higher voltage headroom. And if we come back to the ESD pad, what we have in the is that we have, since we have, especially for the diode connected transistor that works as a clamp, they have noise substrate coupling. So it is coupled to the substrate and also in this case on the ground. So you cannot have a coupling between the PMOS switching gates, the M1 and M2, and also the substrate, and also with the ESD. So that's one of the reasons. So it has more impact on the PMOS due to this.
So it's let's say a topological issue. The fact that you are using stack transistors in PMOS rather than the other one.
Yeah.
In the sense that and the way you connect PMOS.
So maybe the one. Yeah. So maybe the ideal solution is especially as this path a general path from the company, because I wasn't really aware that we needed like forcing the paths for tape out.
Okay, it's okay.
Yeah.
So it didn't get really.
I don't
but at the same time, I understand it was enough for me to understand that it was a topological aspect in the end.
So maybe
nothing connected with specific sensitivity of the transistor.
Yeah, exactly. So one solution may be the PMOS instead of the gates connected to the ground, maybe connected to another point and solve. Yeah.
Thank you very much.
Thank you, Professor.
Thank you very much.
Thank you, Professor. Thank you.
So we go to the next reviewer, Professor Avila.
Thank you. I'd like to thank the team from Bordeaux and the NSP team to invite me for this thesis to be the reviewer of works.
Thank you.
I was invited an opponent in Finland and in 2 hours or 3 hours for patient. So I tried.
You have to try.
So congratulations also, like, the work is very huge, very interesting. Especially you've done a very nice state of art today. So I like your work and also enjoy to read manuscripts.
Thank you.
So congratulations for this work. It's impressive.
Yeah, thank you.
The director says that you do everything that is inside you. Most part of the work is
Yes, yes, I understand. Yeah, yeah, thank you. Yes.
So you see some question in the report,
Yeah.
for example, for in a lot of people, sometimes from different from publication to so on. So, for example, in the last table, when you change the compared to publication, you always the same form with you.
Yes. So what I have by going through the state of the art, I have identified actually true figure of merit that's used in the. Actually, the true ones they are kind of the same, just how I think it's the phase noise is and the logarithm are used. But this choose expression gives the same absolute value. One it gives a negative, and the other is absolute. So for my state of the art, what I have done is for the ones that use this expression, I keep it, and the ones that did not use this, yes, I use this one. So the ones that doesn't use this one, I calculated myself for the table. Yeah.
So, the question from Domenico, do you use the consumption of
No.
the buffer inside?
No. So normally in the state of the art, authors don't put the buffer. So in this case,
I have this question. I said, this.
Yes, it's fine.
It's not this question. So the bow is like a piezo, something like that.
Yes.
So yes.
Okay.
If you do vibration, because some piezo have some answer, the sensitivity to vibration. Is your circuit sensible to vibration, for example?
That's
Because
very
you
important.
change the frequency and shift.
Yeah, that's very important question, Professor. In our work, we do not analyze the vibration, but that's why I put the features perspective of the analysis of the packaging, because for more industrial view or even academic for the robustness,
Yes.
integrating, for example, the ball inside the chip, we need to very carefully analyze the mechanical. So in our work, we did not analyze the
We
mechanical
could
part.
have some can have some vibration. Is
Uh,
that you mean?
in terms of our setup, I don't think so. But in terms of integrating
Yes, it
inside,
could be.
yeah, it could be. So that's why it's an important thing for future work. Yeah. Yeah, it's very important. Yes, because it's very piezoelectric in the end. Yeah.
Yes. I read in a thesis, I think you write, you have a more higher voltage swing using the code base than
A bit, yeah. Yeah.
you don't how I don't know really understand that points. You have full swing in the oscillator. You really control the amplitude at the.
Yeah. Because
You do not go to the saturation of the NMOS transistor in terms of condition to oscillation, right?
the point is maybe this one is okay. Yes, is that the oscillation is where it plays a lot of roles. And
Then
one
you have small signal.
for at the output of the wall, actually the output we are taking from the gate, which is connected to both, so amplitude around 6 to 7 meters. So in terms of before entering the buffer, and why not higher? An easier response is because of the say of the operating area of the transistor. If we go higher for robustness and long term, even in industrial view, product view, and break the transistor. So we keep enough voltage for our performance. Yeah.
So me, I'm most analog designer than digital and from low frequency.
Yeah.
I was obliged to study RF circuit because I have some colleagues from Marseille and from Bordeaux, high frequency. So we have a lot of curve that in frequency domain or fast transform domain, and I see any vision of the oscillation versus time. You take, you don't have any oscilloscope, high-speed oscilloscope that you can see the input oscilloscope versus time.
The measurement or
For example, would be good to see.
yeah.
Well, of course, we see the spike.
Yes.
Give us an idea of the
Okay, the waveform. Okay. Okay. Yeah.
The THD, it's okay.
Yeah. Okay.
Yes, we have a difference between simulation and phase noise. QRS for the PMOScope, it's 145 and 135. You have a 6 dB shift between measurements. So it is in dB. So we switch in dB. So it's very huge, in fact.
Yes.
And you said it's
one of the main reasons
it could be come from the pad, something like that. Are you sure of that? Or
I very one of the come from the pad, and other maybe needed to modelize a little bit better, maybe routing lines and everything. But main of the difference is for the scoping with pads. But we have seen also analyzing.
I have some. And I was wondering about the fight noise, the effect of the power supply to the fight noise indicates the some regulator like that. And I know that the power has a huge, could add a huge effect to the fight noise. That or do you work on that?
Very important question. Yeah, very important question. Maybe I think I didn't explain here and in the face, but we have added a for the mirror, so that filters out the noise supply for the noise. Yes, and it's around 100 kilohertz. The 3 dB copper frequency. So it was something that we integrated. Also, in terms of simulation, even though we are not using here an LDO, for example, I have as a colleague a noise model from LDO just to allow us to analyze in terms of simulation, even though it's not what we are using, but we integrated some supply noise in order to see the effect of C filter. Yeah. This is the photo of the.
And if you can go to the slide 16.
16? Okay. Yes.
You write that the entry on 3 and 4 boosts the negative resistance.
Yes.
But I think they create.
Actually,
if you remove entry on 4, you have a negative.
Yes. Actually,
to see what.
Yes. Yes. The idea is maybe I wasn't clear on this point. Is that when we compare the qualities by using, for example, an LC tank, actually it's still the same because the ball here for the quality it operates in between FS and FP, so it has an inductive behavior. So the ball it's inductive here and it has it resonates with C1 C2.
It's due to the model.
Yes, so the model of the ball allows us to operate it as an inductor, and then the quantities N1 and N2, as you can see here, for the GM it resonates, but maybe requiring a higher power consumption due to the traditional, we'll say, more conventional negative conductors. But with the GM boosting here, we have this factor, this big factor that boosts the negative conductance. And yeah, so it helps to alleviate some in terms of conception and structure constraint.
And could you remember me why you would pay more higher performance with SCGL technology?
Sorry?
SCGL technology, ICS.
ICG. Oh, yes, sorry.
So we found better performance.
Yes.
Due to
Actually, for one of the main reason HPT, they have lower noise.
and we can use GM divided by this.
I never is the investigator, but it's true, Professor, that I think for noise performance, the HPT they have lower intrinsic noise in terms of the signal. So, but on the other hand, they need a higher reception and power, everything. So it's a kind of a balance. But I think from what I understand, the IG they have by consumes more, and they have lower noise. Yeah. And
into GMO, right?
Yes.
And
yeah, maybe it works,
You
but
have the gate,
the collector current,
the base source.
yes.
Because in order to it could be
But you still have phase gate resistance here.
Yes.
So no.
I couldn't really respond because I did not investigate it.
No, I understand. It's
Yeah.
just for
Curiosity.
connection together.
Yeah. Okay.
Now, like a colleague, because after
Okay.
I don't want to go into entire the noise situation. GM, okay, I write my opinion for that.
Okay.
You do a very nice job. You try to define the size noise taking into attention ID. So my question is very general.
General.
Do you think we have a real correlation between the measurements and this equation? You know, because there is a large number of parameters, so I can ask you to draw in GM versus noise, compare simulation, measurement, theoretic.
Yeah.
It's my own opinion. Formula to give ID to choose current, the power, where it comes from the noise, something like that. But I think we are always far from this. We are always far from simulation to this equation. Are you okay with that?
I think.
I want to have your.
Yes, I think maybe I have also stated in the thesis, but I agree in this point is that the main idea of this phase equation is not to have a direct model of the phase noise, more to find the key parameters, key impacts. Why? Because if I really want to have a expression like this and to that it works, everything, the GMAD, I need really go through the PDK and everything to further validate the model and everything, which is really out of scope for the time for the PhD.
Your perspective. Sure.
Yeah, maybe yes, it will be interesting. Yes, exactly. But that would be really more a technological view of the PDK and everything. Yeah. So here.
On this last. Maybe we can have a follow-up discussion later. It could be even easier to understand these, and I will tell you later about why and how you can make it slightly better.
Okay.
Without going on through the level of complexity that you mentioned.
Okay. Thank you.
So finally, like you find that most structure is better than the most in terms of noise.
Yeah.
So very good work. I am very happy to be here. I want to see your presentation, read your paper, and see the change. And it's finished for me. And
Thank you very much. Thank you very much, Jeremy.
Thank you.
So we go to the next and with Thomas Bouchen from NXP.
Yes. So first, I just want to say your work, of course. Just one question. If you would like to embark this kind of technology through radar chip, the main point how we think we will develop.
So yeah, very important question, and I will link that my answer to what both professors have emphasized on terms of the ball. So it's really the mechanical part, because now we are wire bonded outside of the chip. It takes place. So place is very important from what I've seen in NXP and from what we care, because it's cost. If we want to do integrate inside the chip, like a flip chip or things like that, the mechanical is very important, as both professors stated, because it can shift the performance, shift frequency, and it needs to be robust, because whether we're integrating in the daily life of the people. So I think the mechanical part will be very important, and it's really out of what we can see maybe in simulation and everything. Maybe more in the validation part, in the lab, and really a bench or approach that we can validate on this part of performance.
Another question is to the specific regulator. Did you study also how the quality of the network, so if you choose a cheaper one with lowest quality factor?
Yeah. Yeah, so that's another important point. For this PhD, actually, in terms of the book, they are mainly found in terms of in the market and the ones that we can buy directly. So there's actually no standalone ball resonator available to buy. So what we have done is to contact suppliers, and actually we have one or two that we had choice, and they have very mature technology. So in this case, the choice was more first of option, second in terms of maturity and robustness of the technology of the supplier, and I think last was really in terms of which one is better, or because what we wanted to do more in this work is to validate our approach rather than we want the best. So in terms of robustness and validation of the work. Thank you.
Thank you very much. Before we go to your advisor and technical advisor, I will give it to myself.
Yes,
because I think first I really want to congratulate you for the usual that you went to this stage. You got steady performance. And we like the fact that you really investigate on physics for noise, so a lot of things, the transistor, and it's all field that you can do here. There is still one missing topic that this is after.
Yes,
and I guess you know it. First, quick question. If you go back to slide 8,
yeah.
You have this specification on the power consumption, less than 2 milliwatts. What is the power consumption of the DDS? I just want to know how much this specification represents regarding
I'm not sure in terms of that, but I can assure you it's kind of nothing.
Okay.
Yeah.
It's nothing. Did you compare the DDS?
I think comparing to the DDS. Yeah.
So, okay, you know that it is 3 milliwatt or 4 milliwatts. It's okay.
For our oscillator?
I mean, for the whole system.
Yeah, I think there will be probably.
Okay.
And one also why lower?
Yeah,
is because we can increase the one of the fix is the supply voltage, because we wanted to follow kind of what the top level system is using. And second, we can improve the current, but at one moment we will break the transistors. So it's very robustness, and I try to keep it low and following also what other authors have done. So try to be in the same realm as in terms of CMOS technology compared to other authors. It's kind of a lot of options, and I think we can stop at this.
Okay, that makes sense. If you go to slide 17,
Yeah, please. 7. Yeah. Here.
Something that, so we don't have the information, but I know it. You never discuss the gainless of the transistor.
Yes.
Never see it. 150.
Yes. So peak oxide, it's in terms of the hundreds.
Yeah.
And oxide below 50 nano. So
okay. Yeah. So you use almost the minimum length.
In this case, minimum length 150 nano. Yeah. And here I use maximum length 50 nano. Why? One of the main reasons, bigger device, we have lower noise, especially filter noise. However, bigger size, more parasitic to manage. And why we choose 2 and the current mirror? Because from our noise analysis, they are the main contributors of noise. And the GNB pair have a low contribution, so that's one balance. We can just put 3 thick oxy device, but they have higher VTH. It won't be robust for 1.45. We can just say, oh, maybe we can cruise to 1.8, but it's not in our spec. So we need the circuit inside the spec and also be robust. So that's one to balance in terms of the technology choice, in terms of the device. Yeah.
Okay, that answers the question.
Thank you.
Go to slide.
Yeah.
Okay, that's the big word. So, define minimum GM. You start with this one.
Yes.
That's on what?
Yes, I didn't show here. I have we have a
specification first.
And also the GM line, where we can see. I didn't put the equation here, but for the in between FS and FP, we have an expression for the loss of the ball resonator. So, and also we have the expression for the output voltage of the colpit, so, which is at the gate of the ball. So, therefore, we can find the needed current. We can define also what's the GM that we need in order to have the minimum to start the oscillation. So that's the things that need to be balanced. And what I call the minimum GN is, in this case, where the equations are equal, but we need to add the margin. So that's the thing.
True. So inside 20, all of this design flow proposed.
Yeah.
Imagine that we run it balanced on simulation, and we find the minimum GM, and we obtain the required current to reach the readout. This is about simulation.
Yeah, this is basic simulation. Yes. Okay. Yes, things for first in the paper for the values. In the
we will start.
Yes.
I want 1 volt of output voltage.
Yeah.
So this helps to determine the value of ID, and the losses help me to determine the minimum GM.
Yeah. Yeah. So then
do this based on simulation.
Yes. So first calculate, then simulation to validate. In terms of
so you have estimated this value based on the theory of the model you have developed.
Yeah. Yes. Because we can just start anywhere, but it's important to have a starting point from understanding the physics or the theory of the oscillator and resonator. So then we can know we have this starting point, and we can see if it works, and if not, well, we need to readjust. Yeah.
So because during the presentation and even in the manuscript, we never compare these models to the simulation. And I think that important that Domenico said, if you go for TPAS, for instance, it's mandatory that all the theory that's interesting you have developed, you compare it to simulation to say, I already have the first order of estimation. and then I do a fine tuning with simulation. This is the way it works,
Okay.
I guess.
Yeah.
Because so far you present your modeling as you use as interpretation of the results, justify what happens.
Yeah.
And I think you should use it for prediction, and then you fine tune it.
Okay.
Because I think you already have all the material, just don't do it. Even if you said I have to extract many parameters from the simulator to run my theory, I think you should do it.
Okay.
Because this is a
Okay.
right? Okay, I think it makes sense. In this design flow, you define the gem overriding you needed based on the output voltage and phase noise and storing conditions.
Yes, and also since the DMID is linked to the VGS, also it's very important for because we just can't have a low or very high like a GM because maybe the circuit won't work because we have a limit of the supply and we have stacked transistors, so we need to also balance in terms of the value that we choose for GMA. So with the best compromise is closer to moderate conversion. So that gives a little bit higher GMID, but it will alleviate more sometimes of the voltage force to the circuit. Yeah.
Step 3, you choose L.
Yeah.
Then W.
Yeah.
So this is going to provide some different parasitics because if you select L at 50 or 150,
yeah.
it's going to add some others, and you have to retune the oscillation.
Yeah. So that's one thing I did not put, to not shift the focus also is because this is for one specific L. So if we have different L's, maybe higher L's normally will be like more like that. So yes. It's also because also higher L, as you mentioned, more parasitics, and also it will impact intrinsic gain, also other parameters. But we fix and also related to noise, the surface size. It's also one choice we define whether that corresponds for the performance we want. So it will be like we sweep the L and we'll have different curves, and then it's a way of choosing the transistor level.
So I think we can finish on this part. Is when you show the design methodology, you definitely have to illustrate it with draw.
Okay.
To show why.
Okay.
You do this way.
Yeah.
Right?
Yeah. Okay. I agree.
I think we're almost done. I have two last very simple questions. 32.
Okay.
The third harmonic is the same, almost maybe
a little bit lower.
Minus 63, 62, something.
Yeah, 70. Yeah, 72.
Normal. Usually, the third harmonic is the same rejection as the second harmonic.
In this case, it's very low, and we have seen also in the simulation that the harmonics are very low. So in terms of spectral resistance, yeah, that's right.
Yeah, the same. But it should be one. Yeah, the original. Oh, we took later. Last is 35.
35.
And for automotive radar applications.
Yeah.
What about negative temperatures?
Yes. So I did not explain the reason. So let me show the test bench. So first, when we start the measurement, we have the Faraday. So the thing is, we have interference, especially at the noise floor, due to Wi-Fi, Bluetooth, because we are around 2.42 gigahertz. And so we needed to find a solution for that. So one of the solutions is putting the DUT inside the Faraday cage. And but the instrument that we have in the lab is like an NF1 pump to put in the DUT, and we can control the temperature. However, it doesn't fit when we close the cage. So we needed to find a solution at last time, on the last moment for the measurement. So this is actually really a solution, dedicated solution that we have developed. by using the Peltier module, and we are using two stacked ones for higher energy transfer and to cool the PCB. However, we can go maximum that we can is -2 degrees. So we choose to keep it at 0. So it's true. For our product point of view, we need to find a better solution in order to go even below 0 degrees. So that's
part of simulation because you have a big correlation between PLS and neutrons. So you go to negative like -14, minus
the simulation. Yeah. Yes, that's another point. Maybe I didn't mention is that first the model that we have for the ball. Let me show. Explain why I want to know. So first, the values that we have for modeling is provided by the supplier. So what I can imagine is from room temperature. In the simulations, actually we are considering room simulation ball, room temperature ball. So what we need to really do is that first characterize the ball from our side in terms of temperature to find the models at -40, 50, 150 for each temperature, extract the model, and then we have one model with different values for each temperature. So
I understand right. That's to be done.
Yeah.
But to check with the model, the ball at 25, the secret at -40.
Yes, because we didn't have the model of the different temperatures.
Okay.
Is it important? Yeah. So
no, but I mean, if it doesn't work with only the negative temperature for the secret, the ball is not a problem.
Oh, yeah.
You see what I mean?
Yeah.
Did you in PLS test it?
I tested with the different temperatures. Yes.
Okay.
It works with 25 degrees model. Yeah. Yes,
okay. Exactly. The remaining work is about the gold model.
Yeah, exactly. So that's, and I think I can link this question to my interpretation of this part. For temperature, so for far-out phase noise, it's very evident. It's like higher temperature, we expect to have degraded performance in terms of noise, but we have done plenty of measurements, and we have always, for lower temperature until 60, it improves, and then stabilize and it starts to degrade. We couldn't find a response for that, and that's kind of the approach that you mentioned now. So it's like we've done every simulation, and we have no problem. We can replicate these results. So I have further insight in terms of the papers, more physics of the ball, and I have found a few papers that comment on the resonator induced noise in terms of when we vary the temperature. You have seen that this is related to the temperature coefficient of the ball. So that's how we find out this explanation. Yes, we have done the work actually Monte Carlo. We have varied temperatures, but always with the 25 degrees. Anyways.
Thank you very much, Estevan.
Thank you, Professor.
And now we go to the guy who follow you during all the PhD work. So we start with Stefan.
Thank you, Estevan. Thank you. Very nice journey we had together. Obviously, I don't have any technical question for you because we work together.
Yes.
I have a general question based on your experience of the 3 years together. If you would have to start from scratch now, what would you say? What do you trust?
Yeah. So first, what we change? We should have defined the ball to start, because in the beginning we wasn't really sure with which supplier to work. I think that's the main thing of the PhD. And second is to have clearer vision of what it requires for the people, because I have more. So since this PhD is a joint collaboration, industrial and academia, I think it's very valuable. And through every experience that I have in NXP and in laboratory, I see both sides of the things. Because in the beginning, I had more academia view. So therefore, for example, for the takeout, I wasn't really I didn't really know that in terms of the path protection and things. So I think I will be more active in asking what are the requirements outside of the numbers, and to have more a clearer vision of, oh, I need to work this, but I have things around I need to also take in consideration. So I think it's more things that are a little bit out of scope of the focus.
Would you change your supervisor?
No, no,
Yes.
no. I won't
He
change.
said to me, yes.
I think as I put in the acknowledgement of thesis, actually, from the professors I have and even the company part, I don't see as a supervisor for you, so Stefan. I see you more as a mentor, and for both professors, they are not really professors for me. They're like really a person that are always there to support, to learn. So I'm very happy and pleased to be part of MS, TIMA, and anything. So that's so because it's not really just work; it's also the personal part, and I feel really like a pleasure working with. Yeah.
Thank you very much, Stéphane. So now we go to Emmanuel from Grenoble. Emmanuel Pistel.
Thank you, Estevan, PhD. I have a question.
Yeah. Yes.
I had a lot of questions during your PhD, so not today. I would like first to thank MXP and so Mr. Rochen and QS for the PhD and to be part of this PhD. And I would like to thank you, Baptiste, to have had the opportunity to be super vision. Second, I would like to thank the members of the jury, so thanks to the reviewers, thanks to Nico, and thanks to Eric, and also Mr. President too. And Estevan, I would like to say that I think that you did a very interesting job which was from the theory, the design, and the test and characterization. So it was a very interesting scientific work. And also concerning the theory, you showed that the PMOS-based topology was very interesting to I think it's very important. It was very interesting to work with you too because you are going to the discussions when we have some competition. Always we say, yeah, we can try that. Yeah. So it's very interesting. It was a pleasure to interact with you and with all the colleagues which were involved in this. Thank you so much. Finally, once again, I would like to thank you and thank you for all this.
Yeah, thank you for your support and everything.
Thank you very much. We finish with Professor Jean-Baptiste Maigret. Jean-Baptiste,
Thank you, Mr. President. So, first, before talking Estevan, I would want to thank the job. I know that the job is. I know you like it. It's a lot. So thank you, and also thank you for the support and guidelines. Very close to Stefan and agree, and we still work together on our topics. So the part of the lab we have, it's a very interesting we have. So I hope it will follow. Thank you, Emmanuel, also because we had a nice collaboration with Conrad for the first time. work together. So to congratulate you for the presentation. Slides are good, perfect in time.
Oh, thank you.
Yes. A question for
a lot of job, yeah, for that, yeah.
Perfect compared to the first presentation you made.
1 hour 20.
I just want to point out the huge amount of work you've done. You say that you have complete circuits, 2 cross-couple and PMOS and 2 colbits. We just have takeouts in 2, but the others are ready. It's not only the schematic design, you have a huge look to your layouts,
a lot of time.
Responses.
7, 8, yeah.
Was those skills of NSP.
Yes.
You did a lot of multi-color. All your circuits are completely done in this. So it's very important to done the PCB.
Yeah.
So you did the measurements, low noise and temperature. So it's quite hard to do. And so you have fully understood the mix between academia and tested both of them. So it's important that you have this complete spectrum of analog and earth designer, which is very rare at this point of your career. So this is for your work and for our relationship. It's very interesting to work and to discuss with you.
Yes.
Theory, you learn me some points. So it was very interesting to come back to the issue. And yeah, part of my PhD student.
Thank you so much. It's my pleasure.
For that, and wish you all the best for the future.
Thank you so much, Professor.
Thank you, Estevan.
So we're done. We have to go in the other room to decide what happens next, and we'll be back in 10 minutes, I guess.
Okay, thank you.
Aller vers un autre. Ouais. Démarrer avec et on juste comme ouais. Moi,
Si, il y a Isabella, une introduction, et les questions.
Tu n'es pas le chef.
C'est comme des clubs qui a Et à un moment, ça.
Au début, c'est il y a un truc. Et pour moi, ça va, et il y a un truc qui se passe avant le. Tu vois, ce qui se passe, c'est un truc qui se passe sur mode art dans je sais pas, je sens une réunion et d'un coup, ça a basculé.
Ça veut dire que c'est de l'évolution.
Et après, c'est bon.
Voilà, c'est d'être arrivé au même moment.
La feuille que vous devez lire. Ok, je l'ai.
So, thank you so much for watching for this happy end. You already know it. But before, I want to give you a couple of to discuss together. So on behalf of the jury, I want to tell you that regarding the presentation, we really appreciate the clear and the presentation and the quality of the support you have provided. And of course, the outstanding performances you have provided through your PhD, right? So this is really some very important mark that we get from this presentation. Regarding the question, that was very nice time, very long one too, but when it's long, it means that there is a lot of things to exchange, and that's good news, right? So the member of the jury really appreciate the relevant answer you provide to the examiner. You also answer some questions from the reviewer in the presentation that was really appreciated. And the overall discussion highlight that you have a high expertise, not only on security, not only on design methodology, but in the context of industrial application, which require additional skills. So for all of these reasons, we decided together to award you from the University of Bordeaux of the degree of the doctor, PhD doctor. So my best congratulations for that first. And because now you're a doctor, there is something to read that you have to follow some rules in the French part, the English one. You read each one you want. Okay. You read in English. So, in the presence of my peers, the completion of my doctorate in electronics in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationships, true knowledge, in my methods, and in my results. Everyone. Oui, bien sûr. And I would just like to thank both professors for coming and accepting to be part of my career and come to Bordeaux for my PhD defense. I would really like to thank NXP for this PhD and also for all the support I had, especially from Stefan and also from my managers. So,
Thomas, and also my president manager Fabian. So in every aspect of a professional and personal part was very support. So that's why I've said in the beginning that I've seen people I work with, such as Estevan, as a mentor rather than a supervisor. And also I'd like to thank Professor Bighe and Professor Sono, because as you have mentioned, every week we have a reunion meeting. But it's not like a meeting, more a place where I can provide my questions, support, and even outside of this moment, both professors were always there as, for help, for support, and open to the discussion. So I would really like to thank NXP, EMS, and also Université de Bordeaux for the PhD. And also Professor Pace, because he was there since the beginning when I have just arrived in France 5-6 years ago. So he was one of the persons that has seen me grow from a student inside the class, now for a PhD, and now working as an engineer. So thank you so much for all the support.
You're very welcome.
And thank you so much for all the colleagues that are here, and for the CSN group and my colleagues that are always there to support inside of our home. So thank you so much, everyone. And also, nothing else. Thank you. Thank you. This is you don't have to say.
My understanding